Well, hoping by the end of this particular PowerPoint presentation, and if you've looked at the previous series circuit, if you haven't looked at the series circuit, you'll really struggle with this one. But hopefully at the end of this PowerPoint and a few exercises and a bit of a little bit of extra homework, hopefully you guys should start to get a few light bulb moments going, okay, I'm starting to understand this. But look, let's have a little run through this presentation here and see if we can understand a little bit more about the parallel circuit. Look, whilst in a series circuit, the voltages in a series circuit are the sum of all the individual voltages around the circuit. In a parallel circuit, the voltage in a parallel circuit is the same as the applied voltage, and we'll have a look at that. Likewise, very different to a series circuit, the currents in a parallel circuit are not the same. They vary all over the place. We'll have a look at that. Resistors in parallel circuits, whilst the formula for that looks quite daunting, it's really quite simple to be able to ascertain the total resistance of a circuit. We'll have a look at that, and then we'll have a look at power and having a look at a few faults. Okay, from the picture on the right hand side there, you can see that there's two 12-volt batteries, and in both of those pictorial views there are three lamps connected in parallel, and the drawing is showing you, or trying to show you, that you can connect each of the lamps directly to the battery terminal posts, or you can connect the lamps in parallel from each of the lamps. But down below that you can see the circuit diagram clearly showing that the lamps are in parallel and to that 12-volt battery. And as we sort of alluded to before, in a series circuit, you could, in a series circuit, if the current was constant through all the loads, that would be known as a series circuit. Well, we can see here that in this case, the current coming out of the battery, let's say the current coming out of the battery is 3 amps, you can see that one of those lamps might be consuming 1 amp, and the other light might be consuming 1 amp, and the other light might be consuming 1 amp. So whilst the current is split, as you can see, down the 3 branches, so definitely not a series circuit, so definitely a parallel circuit. The other giveaway is that, look, assuming it's a 12-volt battery, you can see that the voltage of each of those lamps is 12 volts, so there's 12 volts, a 12-volt potential dropped across each one of those lamps. So the takeaways here are the current splits down each of the branches, and the voltage remains constant across each of the loads. Simply reiterating that if you were to get a voltmeter and measure the voltage across the 12-volt battery, you would read 12 volts. You would also read 12 volts across each of the lamps. Electrical diagram confirming that the 12-volt battery voltage appears across each of the lamps. As we've said on a number of occasions, in a series circuit, the current in the circuit is constant throughout all of the individual resistors or loads. As this is not a series circuit, this is a parallel circuit, this diagram is trying to tell you that the sum of the currents in the loads is equal to the total current. So you can see that the current flowing through the 10 ohm resistor, for instance, is 1 amp, and the current flowing through a 20 ohm load is 0.5 of an amp, and the current through the 100 ohm resistor is 0.1 of an amp. So therefore the total current flowing in the circuit from the 10-volt supply must be the additions of the branch currents. So Yeah, so whilst the voltage in a parallel circuit is presented across each of the load, the 10 volts is across each of the resistors, R1, 2 and 3. The voltage remains constant, but the current branches down each individual branch. So just take a moment to have a look at this little supply here. 10 volts across each of the loads. 1.6 amps is the total current at junction number 1. 0.1 of an amp flows through the 100 ohm resistor. Remaining current of 1.5 amps continues on to junction 2, whilst 0.5 of an amp flows through R2, which leaves 1 amp remaining to flow through R3. And of course, on the way back to the negative of the battery, the currents join up again to equal 1.6 amps. So whilst in a series circuit, if you are to insert an additional resistor or an additional light bulb into a series circuit, the current will decrease because the resistance of the circuit increases. In a parallel circuit, when you add an additional load, that load will consume some additional current from the supply, and because it's in parallel, that current is added to the total current. So adding another resistor in a parallel circuit increases the total current. Therefore, the total resistance of the circuit must decrease. We'll see that soon in the formula. So but the key takeaway here is if you add resistors in series, the resistance increases, but if you add resistors in parallel, the resistance decreases. So we can calculate the total resistance using Ohm's law, V is equal to IR, and if we were to transpose that to R is equal to V on I, and we knew what the voltage through a resistor was, the voltage across a resistor was, and the current through that resistor, we could simply work out the value of that resistance. Or indeed, if we used the total applied voltage and the total current, we could work out the total resistance of the circuit. A horrible formula, but actually looks a lot more menacing than it really is. If you had watched the previous video, I actually give a demonstration on how to use the 1 on X button on your calculator, which actually makes the formula, which I've highlighted in yellow, really very easy. It looks a lot worse than it is, but essentially if we are trying to calculate the total resistance of a parallel circuit, the formula in yellow is used, and when you are using your, just to recap, when you're using your calculator, you should be able to look. Let's say we're trying to add up a 100 ohm resistor in parallel with a 200 ohm resistor. The method of doing that is simply putting 100 into your calculator, pressing the 1 on X button, and then putting the 200 ohms into your calculator and pressing the 1 on X button, adding those two numbers together and pressing the 1 on X button, and that is the answer. But I'm sure you've worked that out by now, and this is just recapping. So just recapping some basic stuff in relation to parallel circuits. The first one is that the voltage is the same across all the components in a parallel circuit. The branch currents can be found by Ohm's law or Kirchhoff's current law, depending on what information is known. The total resistance of a parallel circuit is always less than the lowest of the branch currents. Trying to explain that to you in the first little drawing, where we have a 10 ohm resistor in parallel with a 15 ohm resistor in parallel with a 20 ohm resistor. if you actually work that out, I'm sure your answer will certainly be slightly less than the smallest resistor, which is the 10 ohm resistor. So the answer will be approximately 8 ohms. I haven't actually worked that out, but if you were to do that, in fact, have a crack at that and see whether my answer is correct. The second little drawing is where we have two 10 ohm resistors in parallel. Now, it's interesting to note that the total resistance will be exactly half of the resistors as long as they have the same resistance value. So if we have two 10 ohm resistors in parallel, the answer will be 500 ohms. It's that could be extrapolated to if we have two 1000 ohm resistors, the total resistance will be 500 ohms. So, and it's when you're calculating this, these sort of calculations out, your level of understanding should be at that level where you are checking your answers as you're working through the problems. It can be seen here that in the drawing below that if we were to have a 100 volt supply and we had three devices, whatever they might be, the first one consuming 1 watt, second 2 watts, and the last one 5 watts. Let's just remember, that power is, in very simple terms, is given off as heat. Each of those three resistors are getting warm and dissipating heat. The total power for the circuit is simply the total amount of heat that is generated by those three resistors. So we can just simply add up the power in the first and second and third resistors. We just add those up, and that would be the total power. Or we could, of course, if we knew the resistor values of those resistors, we could use Ohm's law, and we could calculate the total resistance for the circuit, and we still have the total voltage, so we could work out the with the current and work out the total power. But look, just to realise that each component is independent of each other. Each branch takes power from the supply, and each branch can be considered separately, and the total power in the circuit is equal to the sum of the individual power, and power is measured in watts, and in very simple terms, watts is in resistors in DC, we can just consider that as heat. As can be seen here, this slide is attempting to show that there are many different ways of being able to calculate the power, and there are lots of different formulas that can be used, and it is simply a matter of selecting a particular formula that works. I must say I particularly just use volts times amps in general terms, because I find it quite easy to calculate the current in a branch current. For instance, the kettle there is 4 amps on 230 volts. The power could be calculated by I squared R, but it could also be calculated by volts times amps, so 4 times 230, whatever that is, just over 1,000 watts. So I'm a simple person, so power is equal to volts times amps to me, but there are many other formulas that can be used. Well, let's consider some faults in parallel circuits. The little drawing down below I've marked up in yellow with a switch and a resistor. So you could see that if this switch is open circuited, there would be no current flowing down the yellow path. The resistor would have no current through it. It would be dissipating no heat or consuming no power. So no work would be done whilst the switch is open. It doesn't affect the supply voltage if that switch is open, and indeed if there were other light globes or other things connected in parallel with that, they would be operating perfectly normally. In fact, that's exactly what you have in your house. You would have your light circuits are all connected in parallel, and different light switches are on in different houses, and that's all works perfectly normal. However, if we had a short circuit, which I've drawn in blue, if you have a short circuit on a circuit, there's going to be extremely large currents flowing, and you probably blow the circuit breaker or pop the fuse or what have you. But if that didn't happen, if you had it connected onto some small batteries maybe, the voltage would certainly drop to zero. So if we close the switch, the blue switch, the 100 volts would fall to zero, and any other loads on that parallel circuit, they would all effectively turn off, or they would, if they were light bulbs, they would dim right down to nothing. So that's what the statements above are trying to say. The two most common faults in any circuits is an open circuit or short circuit. An open circuit in one branch does not affect the other branch. That's the yellow setup. A short circuit in any branch affects the entire circuit, as the supply voltage would fall to zero.